In this lesson, we'll talk about systems of linear inequalities in two variables. Remember, an inequality has infinitely many solutions, so instead of presenting them algebraically, we like to graph them in the system of coordinates. This time, we'd like to graph the solution set for the given system of inequalities. So, aside of the skills of graphing the solution set for each particular inequality, we need to recall algebra on sets. For instance, here we deal with two inequalities connected by this brace to treat them as system of inequalities. And if you see a brace like this, the connecting word between the two inequalities is and. Both of these inequalities need to hold in order for the system to be satisfied. So let's keep this connecting word and in mind, which, as we remember, indicates the intersection of two sets. If, for example, this is the solution set to the first inequality, and that's the solution set to the second inequality, since both inequalities are connected by the word and, we are obligated to leave the final answer as the intersection of these two solutions. Okay, so let's draw the solution to the first inequality. How do we do that? We graph the related equation. So let's solve this inequality for y. Y would be bigger equal negative x plus 4. And then we graph this line. The y-intercept is 4, so it's here. And slope is negative 1, so we go 1 across, 1 down, and down, and down, and down, and connect these points. Since we had equal sign included, then the line that we use is solid. And now is the shading part. Y is above the expression that represents the line. So y values are above the line, therefore my shading should be here. All the points above the line are the solutions to the first inequality. Okay, let's look at the second inequality. The related equation is y equals 2x. So it comes through 0, 0, and the slope is 2, so 1 across, 2 up, and again to the bottom, and we connect these points by a solid line again because we have equation included. So that's the line. Now the shading part, y is below the function. Y is smaller than 2x. So everything that comes below the line should be shaded. That's the solution for the second inequality. Okay, but that's not all what we need to do. Now we need to answer the question, which points of the plane are actually solutions to the system of inequalities? So, since the inequalities were connected by the word and, we're talking about intersection of the two solutions. Intersection means common part. That means the region that is shaded blue and green at the same time. Okay, that's this region. Let's mark it in red as a final answer. We also need to look at the edge. Make decision as to the border. Let's look at the intersection point of these two lines. This point belongs to the blue line and to the green line, so it must belong to the solution set. Also, this part of the green line is in the blue region, so it belongs to the solution as well. Similarly, this part of the blue line is in the green region, so it satisfies both inequalities, therefore it's in the solution set. So this red region, together with the boundary lines and together with the vertex, is the overall solution for the given system of inequalities. When you graph it on paper, make sure that your final solution is marked either by different color or draw it a lot stronger, so it will be clear for the reader what you had in mind as your final solution, and be further specific about either including or excluding certain parts of the boundary. Also, watch the vertices. Should you include it or should you exclude it from the final answer? So in our case, the final answer is the region marked in red. Any point from the red region, when taken and plugged in to the system of inequalities, will satisfy both inequalities. Therefore, it will satisfy the whole system. Okay, let's look at the second example. Again, let's rewrite this inequality by isolating y, so it's y bigger than negative x plus 4. And obviously the related equation will be y equals negative x plus 4. So when we graph this line, We start with 4 as a y-intercept, and we go by the slope -1. So 1 across, 1 down, like this. And since we didn't have equation in the original inequality, this time we need to use a broken line. Let's join. As before, let's make the decision which half a plane should be shaded. Since y is larger than the function, larger means above the line, so that's the shaded region. Okay, so the solution to the first inequality was marked in blue. We're going to use green for the second inequality. Again, the related equation is as in the previous example, just y equals 2x. So we can easily graph it, starting from 0, 0 and going 1 across and 2 up. Okay, again, we don't have equation included, so we use broken line. Let's join. And finally, decide which half a plane, this one or that one, should we shade. So y is smaller than the function. So y is below the line. Below the line means this bottom part. So let's shade it. That's the green region. As you see, both lines and both regions are actually the same as in previous example. What's different is the connecting word or instead of and also no equation. So the no equation part we already accommodated by using broken lines. What about this or part? Well, we're looking for either blue solutions or green solutions. Recall in Venn diagram, if this circle represents the blue solution and that one the green solution, the or part will be everything what's in one or the other circle, all together. Therefore, this is a union of sets. That was the intersection of sets. Now we're talking about union of the solution sets. Okay, so using the red color for the final answer, the union means I should shade stronger either blue or green. They don't have to be both together. Either this or that. That means everything what's here and there and there and there, all this region is the solution set. What about the boundary lines? Since this was a dashed line, broken line, that means any point on this line does not belong to the solution of the green inequality. Since this part of the line was not in the blue region at all, that means those points will not satisfy this inequality either. Therefore, those points have to be excluded. They don't satisfy neither of those inequalities. Okay, let's draw the stronger broken line in red. Final answer. Similar justification is for this part of the blue line. It does not belong to the green and also does not belong to the blue region because it was a broken line. It's still broken in red. Finally, make decision about this vertex point. Well, this point doesn't belong to neither of those lines. Therefore, what we're supposed to use is an open circle here to indicate that yes, we checked it and this point definitely is not among the solutions. So overall, the solution set for this system of inequalities is this whole red region except for the border lines and except for the vertex. Next, we have this system of inequalities. What is the connecting word? Yes, it's and. Since it's and, we're talking about intersection of the two solution sets. Okay, let's write the related equation first. Y equals 1/3 x minus 2. And we can quickly graph it. Starting from -2 on the y-axis, go by the slope 1/3, 3 across, 1 up, and to the left. So those 3 points need to be connected by what kind of line? Dashed line, because there's no equation here. Let's connect it. And now let's shade the proper region. Since y was smaller than the function, therefore the points to shade are below the line, lower than the line. Obviously, you can always take a test point and double check this. But as long as the inequality is implicit, that means we have y on one side and the function on the other side, it's really easy to use this intuitive geometrical interpretation. Y coordinates are below the line, so that's why we mark below the line. Okay, the related equation for the second inequality is x equals 0. Well, x equals 0 gives us the y-axis. And since equation is included, we graph this y-axis by a solid line. Now, which half a plane should be shaded? To the right of y-axis or to the left of y-axis? X is larger or equal than 0, so x's are to the right. They are higher than 0. Okay, so finally we're taking intersection of these two sets, the purple and the orange. Intersection means common part, so let's highlight the common part, this region here. And let's think about the borderline. When I look at this section of the y-axis, it is in the orange region, but it's also in the purple region. That means it satisfies both of these inequalities. So yes, I should mark it in red. What about this vertex point? It belongs to the orange, but it does not belong to the purple. Since it does not belong to one of the set, it's not a solution of the whole system of inequalities. So what I need to do is to put an open circle like this to indicate the vertex will not be taken. And this part of the borderline, as you see, it does not belong to the purple solution, therefore it can't belong to the overall solution. Again, broken line, make it in red. Dashed line like this. So that's the overall solution for this system. And the following example, this time the connecting word is or. The first inequality has related equation y equals 1. So if y is 1, it comes through this point and it's a horizontal line. It is a solid line because the equation is included. Let's graph it. Since y must be larger or equal than 1, we should shade everything that is above. Those are the points with y coordinate higher than 1. So I will shade it like this, everything starting from this line up in this color. And second inequality. This time, if we write the related equation, it is 2x plus 3y equals 6. And this equation is given in standard form. So what we can do, we can find out x and y intercept. If x is 0, then this part disappears and we have to solve 3y equals 6. So y by itself is 6 over 3, which is 2. If y is 0, then that part disappears and the resulting equation is 2x equals 6. So x equals 6 divided by 2, which is 3. So here are our two intercepts. Let's mark it in the diagram. 0, 2 is over here and 3, 0 is here. So that's 3, that's 2. What kind of line? Solid line. So let's graph it. And now, since this inequality is not given in an explicit way, y bigger or smaller than something, so this time let's take a test point. Let's choose 0, 0, the easiest point to check. If I plug in 0, 0 to my inequality, I have 0 smaller equals 6. True or false? Well, it's true. 0 is indeed smaller than 6. Therefore, the solution set of this inequality is the half a plane that contains this point. Let's shade it then, all this region. And now I reserve red color for the final answer. So orange or purple. Everything was shaded in orange or purple. So the only thing that is actually not shaded is this tiny angle on the right side. Okay, everything was here and there. So this part for sure, and over there and here, everything until the corner. And as usual, we need to decide what about the edges, what about the boundary lines. Since we deal with the connecting word or, we're talking about union of two sets, so as long as the line is solid and it's either in purple or in orange, it will be taken as our final solution as well. So this part is taken and that part is taken. Therefore, the vertex is taken as well because it belongs to both of those lines. So it has to be marked by a covered dot. Okay, that's the whole solution. Let's practice some more inequalities. This time we have absolute value inequalities. So in order to graph them, the first step would be to rewrite them with no absolute value. How do we change this absolute value inequality to the system of inequalities. Remember, if something is smaller than 1, that means the something oscillates between -1 and 1. It works like this. And the something will be written with no absolute value anymore. So that's the way how we resolve this inequality. If you don't remember this fact, check one of the previous videos on absolute value inequalities. And then we can solve this system of inequalities by, for example, adding 2 to all three sides. So the x by itself would be enclosed by -1 plus 2 is 1, and 1 plus 2 is 3. Which means we're looking for points with x coordinates between 1 and 3. We don't have any information about y coordinates, but we're searching for the solutions in a plane, not on the number line, but in a plane. So that's okay. X between 1 and 3 is here from 1 to 3. Okay, but the y can be anything. So any point from the segment from 1 to 3, but stretched by possible y's. So the intuition tells me it will be such a channel. Well, let's see if this intuition is correct. How can we do that? We need to realize that this system of simultaneous inequalities, that's the same as two inequalities written with the connecting word and. First inequality is x is smaller equal than 3, and also x is larger equal than 1. So our original absolute value inequality is equivalent to this system of inequalities. The related equation for the first inequality is x equals 3, which is a vertical line. It's a solid vertical line coming through 3. Let's graph it. And the related equation for the second inequality is x equals 1. Again, vertical line coming through the point 1, a solid line because equations included. Let's graph it again. Okay, so yes, we have the border lines like this. Since our x oscillates between 1 and 3, it's pretty obvious that our points must be inside this channel. But if we don't see it here, we could shade it the regular way. That means for x smaller equal 3, we'll shade everything that is to the left of 3, and we'll shade it in green, like this. That's first inequality. And the second inequality, x larger equal than 1, okay, that must be everything that is larger than this 1 level. That means this way. Since we're taking intersection of these two because the connecting word is and, then you can see clearly that the region that is marked in both blue and green is inside this channel. Should we take the border lines? Since this border line is in green, that means it satisfies the first inequality, but it's also in the blue region, so it also satisfies the second inequality. So yes, it will be taken to the overall solution. Similarly, this blue line, first of all, it is blue, so it belongs to this inequality, but it's also in the green region, so its points satisfy the first inequality as well. Therefore, it has to be taken for the overall solution. This is a bit longer, but results in the correct answer. If you notice that x oscillates between 1 and 3 at this stage, you could draw it at once, the final solution, just the red channel. Our answer is in red. One more inequality, this time something in absolute value is larger than 3. That means that this something is either smaller than -3 or, connecting word or, this something is larger than 3. Again, if you don't remember this, check the video on absolute value inequalities. So if we solve those inequalities for x, x would be smaller than -4 or x is larger than 2. Okay, let's graph the inequality x larger than 2. The 2 is over here, and the inequality is strong, so we don't have the equal sign, therefore the line should be broken. And we should shade everything that is larger than 2, that means to the right of 2. Let's shade it. That's the solution set for the second inequality. What about the first? X is smaller than -4. The -4 is here. Again, we don't have equation, so we draw a vertical dashed line coming through -4. Let's do it. and our x's are below -4, so everything that is to the left of -4 should be shaded. Okay, since the borderlines are dashed, they won't be taken for the final solution. And this time the overall solution is whatever we see marked so far, because the word OR is telling us to take the union of these two sets. So both of these sets will constitute solution to the original inequality. And since we reserved the red for the final answer, let's shade it again in red here and there with no border lines. So to indicate that there is no border lines, we need to mark this dashed line in red as well. Here it is. In two more examples. These are a little bit harder, but what we need to do first is to drop the absolute value. That means to rewrite this absolute value inequality in a system of inequalities with no absolute value. What does it mean that something in absolute value is smaller than 3? It means that the something is enclosed by -3 and 3. If I want to rewrite those inequalities, it will be x minus y smaller than 3 and x minus y bigger than -3. Since it will be easier to graph if we will have inequalities given in an explicit form, that means starting with y, let's rewrite it again. If I move y to the right and 3 to the left, I will obtain y larger than x minus 3. So let's write it, y larger than x minus 3. And similarly with the second inequality, y goes to the right and -3 to the left. So y would be, reading from the right, smaller than x plus 3. So in the end, we really need to graph this system of inequalities. Let's start the first one. Let's graph the related equation y equals to x minus 3, starting with the y-intercept -3, which is here. And we're going by the slope 1, so 1 across 1 up, like this. We need to connect those points by a dashed line because there is no equation here. So let's connect it. And now we are going to shade in brown y larger than the function. So all the points with y coordinates above the line. Therefore these points. Okay. Now for the second inequality, the related equations y equals x plus 3. So we start with y-intercept 3 and again slope 1, 1 across 1 up and 1 down, like this. Again, we use broken line because there's no equation. Let's graph it. And purple shading, y is below the line. So everything that goes down like this, below the purple line, will be shaded. Okay, for our final answer, in red, we're taking intersection because these two inequalities are connected by the word and. So intersection is this inside channel between these two lines. So that's our final answer in red. What about the border points? Since both lines are dashed, we'll still have dashed lines for the overall answer because that means that those points do not belong to at least one of the sets, and that's not allowed. We have to have points that belongs to both sets. So dashed line for the overall answer as well. Second inequality, I would encourage you to try it on your own first. Let's rewrite it with no absolute value. So absolute value of something is bigger or equal than 2 if either this something is smaller or equal than -2 or this something is bigger or equal than 2. It's farther than 2 steps from 0. So either to the left, farther than -2, or to the right, farther than 2. And now let's solve each inequality for y to rewrite it in explicit form. So that will be -x minus 2 or y bigger equal -x plus 2. Let's graph this line first. So the related line is y equals -x plus 2. Starting with the 2 on the y-axis, the slope is -1, so 1 across 1 down like this. Let's connect those points by a solid line because equation is included. Which half a plane should we shade? Y is larger, that means it's above the function. So y larger than the line is here. That's the solution. And then maybe in purple, again the corresponding line is y equals negative x minus 2. So we start with negative 2 on the y-axis, and we go by the slope negative 1. Again, 1 across, 1 down, and a couple more points here. Equation included means solid line. Let's join it by a solid line like this. And which half a plane should we shade? Y is smaller than the formula for the line, so it's below this line, so it's here. Now, since the connecting word is or, then we are taking union of these two sets. So the final answer will be all this and that region all together, including the border lines. Why? Because each point of the line belongs to one of the sets. Those points belongs to green and these points belongs to purple. So they satisfy at least one of the inequalities. Therefore, they satisfy the original inequality as well, because of the connecting word or.